All right, let's take a high-speed tour of the universe of galaxies. And I promise you, these aren't just some pretty, fuzzy smudges of light in the sky. Nope. They are vast, they are complex, and, as we're going to see, they're often incredibly violent systems. So, let's just dive right in.
So here's the big puzzle for today. You look out into the cosmos, and you see all these galaxies. Some of them are just kind of quietly doing their thing, forming stars, but others are absolute monsters, raging with energy and outshining everything for billions of light years around. So what makes the difference? What turns a galaxy from quiet to monstrous? Well, to figure that out, we've got to start at the beginning.
First up, we need to get one thing straight. Galaxies and stars are two completely different beasts. I mean, they're not even in the same league. Stars are, well, they're pretty simple, but galaxies are a whole other level of crazy.
You know, the contrast is what's really fascinating here. Stars are pretty much all the same, right? They're spheres of hot gas, and you can define them by their temperature and how bright they are. But galaxies? Oh man, every single one is unique. They come in all these different shapes and sizes with totally different populations of stars. And unlike stars, they're constantly crashing into each other, playing this huge cosmic game of gravitational tug-of-war.
So to try and make sense of all this chaos, astronomers needed a system. And that's where Edwin Hubble comes in. Back in the 1920s and 30s, he came up with a classification system based purely on what these things looked like. It was kind of like a cosmic sorting hat, the very first step in trying to organize this absolute zoo of galaxies.
First up, we have the ellipticals. And honestly, these are the dull, fuzzy balls of the universe. They're basically giant retirement homes for stars. They're packed almost entirely with old, reddish stars, and there's no gas or dust left. That means no new stars are being born. They just kind of exist.
And then you've got the spirals, like our own Milky Way. And these are the complete opposite. They are active, they're dynamic, they're alive. They've got that bright central bulge, a big flat disk, and of course those beautiful, iconic spiral arms. And because they're full of gas and dust, star formation is this vibrant, ongoing process.
And we can get even more specific with these. Hubble subclassified spirals from A to C. So an SA-type galaxy has this massive central bulge, and its arms are wound up so tight they look kind of pathetic. But then you get to an SC galaxy, and it has this tiny little bulge, but these spectacular, gorgeous, loosely flowing arms. Just beautiful.
And finally, if a galaxy isn't an elliptical and it's not a spiral, well, it just gets tossed into the irregular bucket. These are the cosmic accidents. They have no real shape because they've been gravitationally mangled and torn apart by flying too close to one of their bigger neighbors.
And just for fun, because you got to let the geek out a little bit, some spiral galaxies have a straight bar of stars running through their center. And some of these barred spirals look just like Darth Vader's TIE Advanced Fighter spinning out of control. Once you see it, you can't unsee it.
Okay, so we can sort galaxies by how they look. That's a great start. But how in the world do we know how far away they are? This was one of the biggest questions in astronomy for a long time, and solving it meant we had to find, well, you could call it the ultimate yardstick for the cosmos.
The secret sauce here is this concept called a standard candle. It's pretty simple, actually. Imagine you have a 100-watt light bulb. Because you know exactly how bright it's supposed to be, you can figure out how far away it is just by seeing how dim it looks from a distance. So the whole trick was finding objects in space that act like that standard light bulb.
The first huge breakthrough came with these amazing stars called Cepheid variables. They're these giant stars that literally pulsate. They get brighter and fader over a really precise regular period. And here's the magic part. How long it takes to pulse is directly tied to its true brightness. So you find a Cepheid, you time its pulse, and bam, you know its wattage. This is exactly how Hubble proved that the Andromeda Nebula wasn't a nebula at all. It was a whole other galaxy, millions of light years away. It changed everything.
Now, Cepheids are great for galaxies that are relatively close by. But for stuff that's really far out there, you can't see individual stars anymore. For that, you need a much, much brighter candle. And that's where Type 1a supernovae come in. This is when a white dwarf star explodes with a very specific, predictable brightness. The only catch? It's a one-time show. You have to be looking at the right place at exactly the right time to catch it.
And all of this work led to Hubble's most profound discovery of all. The farther away a galaxy is, the faster it's moving away from us. This relationship, Hubble's law, proved that the entire universe is expanding. The classic analogy is raisins in a loaf of baking bread. As the dough expands, every raisin sees every other raisin moving away from it. and the ones that are farthest away seem to be moving the fastest. Our universe works just like that.
So, now we can classify galaxies, and we can measure how far away they are. Let's get back to our central mystery. Why are some galaxies quiet, and why are others these violent monsters? The answer, it turns out, lies deep in their hearts, with something we call the central engine.
So what's the trigger? What kicks this whole process off? In almost every case, it's a collision. When two galaxies merge, their gravity just wreaks havoc. It starts compressing these enormous clouds of gas and dust and funnels it all down toward the center of the galaxy.
One of the first results of this is something called a starburst galaxy. Now, the name sounds super extreme, right? But it's all relative. A normal galaxy, like our Milky Way, it might form, say, 1 to 3 new stars every year. A starburst galaxy might crank that up to 10 times faster. So it's a big burst for sure, but is nothing compared to what comes next.
But the real monsters, those are the active galactic nuclei, or AGN for short. This is what happens when all that gas from a galactic merger funnels all the way down onto the supermassive black hole at the galaxy's core. As all that matter spirals in, it forms this superheated glowing disk, an accretion disk, that can literally outshine all of the billions of stars in the host galaxy combined. And some of that material gets blasted out in 2 powerful jets, like a cosmic blowtorch, moving at nearly the speed of light.
Now here's the really clever part. For years, we saw different kinds of AGN, like Cepheid galaxies and radio galaxies, and we thought they were totally different things. But it turns out the AGN unification model explains them beautifully. They're actually the same object, we're just looking at them from different angles. If you're looking at it face on, you see that brilliant bright accretion disk. But if you're looking at it from the side, a big dusty donut shape blocks the disk, and all you can see are those colossal radio lobes being powered by the jets. It's all about perspective.
And that brings us, finally, to the most extreme, the most luminous, the most powerful version of an AGN in the entire universe, quasars. These things aren't just active galaxies. They are lighthouses, beaming at us from the very dawn of time itself.
Just let this number sink in for a minute. A single quasar, which is just the tiny point of light powered by that black hole, can be over 100 times brighter than its entire host galaxy, a galaxy that contains hundreds of billions of stars. That is an absolutely insane amount of energy coming from a region of space no larger than our own solar system.
The energy output is it's incomprehensible. As the source material says, everything in the immediate vicinity of the quasar is annihilated. It's so powerful that matter itself is just converted directly into pure energy. These are, without a doubt, the most destructive engines in the entire cosmos.
But how do we know they're these echoes from the early universe? The proof is in their enormous redshift. Because the universe is expanding, light from objects that are super far away gets stretched out on its journey to us, shifting it to longer, redder wavelengths. Quasars have some of the highest redshifts we've ever measured, which is ironclad proof that they are billions of light years away. We're seeing them as they were when the universe was just a baby.
And that's really the final crucial takeaway here. Quasars are a thing of the past. The universe back in its youth was a much more violent, chaotic, and gas-rich place. There was plenty of fuel to feed these monsters. They don't really exist in the same way today, which is what makes them so precious. They are perfect cosmic fossils, shining lighthouses that let us look back across billions of years and see the universe in its infancy.